Okay, there we go. Answers to your homework. Answers to your homework. 2.7a. Does this look like it, right? Just switch these two. Okay. I hope number one and number two are pretty easy because all you had to do is just switch those. So hopefully that was an easy type deal. The graphs sometimes give me difficult, but again, I just find points and switch those points and plot those switch points and then somehow connect them to where it looks somewhat inversely. So this is the red one is the one that it should be. The red one went right along with it here. Kind of follow the closed spot and the open spot. This point goes to here. It ends up at the same spot. Most definitely, this is the type of problem you're going to see on a free response, solving for the inverse. Notation is as important as the actual answer, right? F inverse of x should be something like x minus 5 over 3. There are other ways to write this that are acceptable. But x minus 5 over 3. Second one should be negative x minus 7 over 2. If you put negative x plus 7, that's okay, over 2. And then the last one, 3 halves multiplied by x plus 1. Again, notation is just as important as anything else. I think technically this one should be y inverse because they just said y equals. That one, and that one should be k inverse. I don't know why they put f on that one. That should be k inverse. Yep.
For y inverse, you just do y
to the negative 1. Number 8 took a little bit more work. So I have negative 2x plus 3 over x minus 1. Again, there are other ways to write that. Negative 2x plus 3 over x minus 1. Number 9 should be h inverse, negative 3x plus 1 over 2x minus 4. 10, y inverse, again, 5x plus 4 over x minus 1. And then 11 should be g inverse, 7x, oh, I'm sorry, all of it's negative. 7x minus 1 over 3x minus 2. There's a reason why they had you do 4 of those. Yes, ma'am. 9. Well, you don't want to, you could factor out a 2y, but you really don't want to because you want y by itself. And so you're okay by doing that because then you'd end up dividing by the x minus the 2, but then you still have to divide it by the 2 again. And so you would have 2 times x minus 2. Again, guys, I told you there's several ways to write this, and I don't know which way's better or worse, but and there's it takes a little bit longer to grade. Just I don't want to say there's 30 possible answers, but there's quite a few possible answers that work. Okay. The notation is as important as anything else because if I don't see the negative 1, you're wrong. And so that becomes pretty easy to grade if you don't do that part of it. But the negative can be distributed. So you could have negative 3x minus 1. I don't know which way is the perfect way to write that, right? And they don't tell you. So there's several ways to write that. Does that answer your question? Okay, did you all hear what she meant by that? She factored, instead of factoring a y out right here, she factored a 2 out, 2y. And it's okay, but then you got to divide by the x minus the 2, but then you still have to divide by the 2 because you got to get y by itself. Beautiful. Okay, so that was that worksheet. The second worksheet, or the second, there was 2 parts, yes? You had to be in, okay. So the first one, you should have got, for number 1, you should have got 15, 2, 5, 3, 2, 4, negative 1, 5, 5, 6, negative 1. 7, 7, 8, 11, 9, 5, sorry, 0, 9, 0, 10, 9, and 11, negative 4. $12, negative 4. 13, 8. 14, 4. 15, 8. 16, 7. 17, negative 3, 7. Should be brackets. Negative 3, 7. 18, negative 4, 8. Brackets. 19, 2. 20, negative 2. 21, not possible. 22, not possible. Beautiful. Questions about anything? Probably going to see a quiz pretty soon. Pretty soon. Told you guys, some of you guys aren't not doing the greatest job on your homework, so I'm going to start making you accountable for homework. So quiz pretty soon. Real soon. Any questions over it? Any questions? Y'all good? Okay. Beautiful. Here we go. 2, 9, 2, 10. 2, 9, and 2, 10. We got to catch up on the day that we spent an extra day reviewing. I think it's pretty easy to put these two together. Again, most of this stuff you guys have seen. You guys have seen logs before. We just got to make sure we incorporate the knowledge that you know already into information. So, well, let me take that off so I can pull that down a little bit. Every operation has exactly one inverse or opposite. Well, that's actually what they said. We learn inverse operations because this will allow us to solve equations using various operations. We use inverses. You guys probably always talked about it being opposite. For instance, if you have addition like x plus 3, you guys know that we subtract 3. Well, subtraction is the inverse. Whoops, I need to write it back down. Here we go. Subtraction is the inverse of addition. This is 3x is equal to 7, which is multiplication. We know that we need to divide. This is not new to us. X cubed equals 7. Well, I want the opposite of cubing something, which is rooting or cube root. Uh-oh, sorry. And then we have 3 to the x. And this is the one that's new to us, or not new to you guys, but it's somewhat newer than what you guys are used to. It's not addition or subtraction. This is an exponential function because the x is to the exponent. The x is not being multiplied. The x is not being divided. It's not being added, subtracted. It's an exponent. And so to undo an exponent is how we do logs. And that's why we have logs. So this is logarithmics, okay, or logs. So that's all logs are. It's just a special way of writing things. I know logs, when I was your age, they just flat confused the heck out of me. I didn't understand what the heck log was. I knew how to work them, but I didn't really understand what it was. And I think that's what makes pre-cal a little bit harder is you kind of just really know, you got to need to know why you're doing what you're doing. Okay? So logs, all they do is undo exponentials. That's what they do. And on the flip side of that, exponentials undo logs. Okay? So recently we learned about exponential functions and their properties. We would like to solve equations using exponential functions, which creates the need of an inverse operation related to exponentials. So the big idea, just as we can write rational functions in decimal form and fraction form, we can also write equations in exponential, or logarithmic. I think it's arithmetic. I think it's logarithmic. This doesn't look like exponential. Exponential. These forms create equivalent statements that represent some or the same claim. We are not changing the problem when we convert back and forth. We are simply rewriting the equation in an equivalent form. So we're not changing anything other than the look. We're not changing the value. We're not changing what it's equal to or anything. We're just changing what it looks like. And this, guys, is what you need to make sure you need to know. This is the exponential form. This is b to the a equals c. So b to the a equals c. And this is log base b of c equals a. Loopy deal? Is that what your teachers did last year? Y'all ever do? So b to the a equals c, loop, b or log base b of c equals a. However you want to do, that's that little loopy deal. If you can get the loopy deal down, I mean, that's either loopy or unloopy. It says notes over there. I don't know if you need any notes. All right, here we go. Example at number 1. Notation at the base of log is base 10. Oh yeah, we do have two common bases or logs. Base 10, which means they won't write a base number there, like it will be blank. And in base E. In base E changes it from log to natural log. So two different bases. They didn't talk about the natural log yet. So convert the following from exponential to logarithmic form. So this is my little loopy deal somewhat. Log base of 3 of 9 equals the exponent 2. Base, this is what you need logs to solve for the exponent. Of course, we're not solving for these, we're just rewriting them. This is like rewriting the square root of 4 equals 2. The square root of 4 equals 2. I'm rewriting this to this. This is log base 10, and you won't see base 10. If you put a 10 there, it's okay. If they're not going to count it wrong, you just don't see it. So base 10 of y equals x. Yes?
So you just assume that a log without a base number is just base 10?
You don't assume, it is.
It is.
You don't have to assume, it is. Yep, anytime they don't write a base number, it's a 10 there. Log base r of w equals t. And then this last one, this is supposed to be log. Now this one's written backwards, so be careful, right? Your loopy deal goes this way. Okay, your loops can go to the right or to the left. This is log base e of y equals 3x. But again, you want to seem intelligent, and you don't want to seem like you don't really know what's going on, and you won't ever see log with a base of e. Because anytime you have the log of base of e, that's the natural log of y is equal to 3x. So natural log, and then the log with no base. Okay, rewriting, get comfortable with it. It's all that log is just a way to rewrite an exponential. Okay. Again, it's nothing that you guys didn't see last year. We just got to take it up a little bit further to make sure you know what you're doing, not necessarily that you know how to do it. Now I want to convert logarithmic into exponentials. And this is almost easier to me because we want a loopy. 7 squared equals x. And I'll just leave it like that. If you want to put 49, it's okay, but just leave it. This one's backwards. Loop you the back way. 3 to the x equals y. I don't see a base here, but you guys got to know 10 to the 2 equals y. And my guess is y'all are done already. This is a e to the 4 equals c. Yes, no, maybe, okay, good. Beautiful. Beautiful. All right, now. Well, I'm almost getting ready to shake this thing. Evaluate the following expressions without a calculator. These you got to know. There's got to be certain ones you got to know. They're not going to put one out there that's really big. They're going to put stuff out there that you should be able to at least somewhat calculate in your head. So this, 2, if you want to make yourself a little loop, I don't know, 2 to what equals 8. So this equals 3. A lot of students, what I used to see on this, guys, I used to see an X here. And so they would say 2 to the X equals 8. And then they would say X equals 3. That tells me you really don't know what's going on. There's no X up here. There's no X. So X doesn't equal anything because there is no X. This equals 3. Just like if I said the square root of 4, simplify that. It simplifies to 2. Log base 2 of 8 simplifies to 3. It simplifies to 3. And really, there's no work to be shown. You should just know how to simplify that in your head. Now, if you got to do something to figure it out, but that should just be a 3. Just like this right here, you should know that's a 2. That's a 2. 5 squared is 25. Next one. Uh-oh, that makes it a little bit harder. 2 to what is 32? So 2, 2, 4, 3 is 8, 4 is 16, 5 is 32. That's probably about the hardest one you might ever see. And after you do it a while, you'll start knowing the 2s. 3s, but they're not going to do like 16s, right? The next one, I have a log with base 10 is 100, and that means you got to square a 10 to get 100. So you should just have a 2 out here all by itself. You got to know how to simplify this stuff. And it should be like instantaneous, just like if you saw the square root of 9. You don't ever leave anything as a square root of 9. You don't ever leave anything as 2/4. You change it to 1/2. You would never leave anything log base 16 of 4. You should know that if I went log base 16 of 4, that means I got to take the square root of 16 to get 4. And the square root exponent is 1/2. The square root exponent is 1/2. And these are things you should know. We just got to get some practice with it. Square root of 16 is 1/2, and the square root symbol is 1/2 power. 3, 1. What do I got to raise 3 to get 1? What do you raise anything to get 1? 0. That's one of the easiest ones to simplify, but it's one of the hardest just because we're not used to seeing it. And that's a good one because that's a base 10, 10. And anytime you have a base 10, 10, or base 2, 2, or base 16, 16, or base 200, 200, that has to be a 1. That has to be a 1. Because there's only, you raise it to a 1 to get the same thing. This next one's a little tough because this is base 6, but this is 1 over 36. So I might treat that as a 36 first, meaning I know I need to square a 6 to get 36. But it's not 36, it's 1 over 36. And so to get a exponent to the denominator, you have to make it to the negative power. So that will be a negative 2. 6 to the negative 2 makes it 1 over 6 to the 2, and 6 to the 2 is 36. So you got to get comfortable with those. You'll see some on your homework, and if it starts becoming difficult, guys, go to your little AI thing and say, I need to find some simplifying logarithmic expressions. Give me 20 of them with no answers. And then do all those 20 and then say, now give me those answers, and you can check. Use your AI to your advantage. Don't use it to how do I do this, unless you don't know how to do it. Use a calculator to evaluate the following expressions. I don't have a clue what I need to raise 10 to get 9. So I got to use a calculator to do that. Have to. There's only certain ones that we cannot use calculators for. Most time we need a calculator. There's more we got to use a calculator for than we don't. No idea what I got to raise 2 to get 9. It's less than 1. Because if I raise 10 to 1, I'll get 10. So it's less than 1. But I don't know how much less than 1. It's not a whole lot. So you just hit your little log button and you hit 10. I'm sorry, you hit 9 and you hit enter. This one. Let me make sure you know how to do different bases. Nobody has a regular 84 in here, do they? The old, oh yeah, there's one. I think it still does it. The old 83s don't. This is math. And down here somewhere, I think it's easier to go up, I think. There's log base. So there's log base 2 of, what was that thing? 10. And it's 3 point something. You should know it's 3 point something because 2/3 is 8 and 2/4 is 16. So it has to be between 3 and 4. And they'll do that for you at some point. They'll say no calculator on a multiple choice question. They'll say no calculator. You think, how in the world do I know what log base 2 of 10 is? Well, they're only going to give you one of those that's between 3 and 4. Kind of fall. I don't know if it's 3.3. I don't know if it's 3.4. I don't know if it's 3.5. I don't know if it's 3.1. I don't know if it's 3.8. But it has to be 3 point something. And so one of those answers they'll give you is 3 point something. They'll give you 4 point something. They'll give you 2 point something. And then they'll might give you not possible, or who knows. So you should know it's 3 point something because 2 cubed is 8. Let me write that down. Oops, sorry, here. Because 2 cubed is 8 and 2 to the 4th is 16, and 10 has to be between 8 and 16. And so it has to be 2 to the 3 point something. So you should at least mentally think about that. And then log base 7 to 135, you just punch and chug, plug in that. Okay? Calculator problems. You kind of need to know how to use a calculator too. All right, now, this is new to you. One useful purpose for logarithms is when dealing with exponential data. Exponential data can be very challenging to display graphically because the values start out very, very small and grow very, very quickly. It's difficult to create displays that effectively show the smaller values along with the extremely large values, right? 2 starts off with 2, and then it goes to 4, and then it goes to 8, and we get to 32, and by now we've gotten too big of a graph because I don't go all the way up to 64. Okay? Yep.
I have a question. Sorry. Go back to example 4. Isn't
Change of base formula. Yeah.
What is
It's just change of bases. Log of 135 over log of 7. I don't teach a change of bases because our calculators change the bases automatically. Yeah, they call it the change of base formula. You can change it to base 10. Used to, our calculators didn't have that little base number. Used to, we didn't have calculators. We had to use tables. That's back in the day. But they don't worry about the change of base formula in pre-cal. So the population of English Americans in the current United States since 1620 has grown exponentially. The estimated population is shown from 1620 to 1820, where t equals 0 represents 1620. I wish they would have made t equals 0 equal to 1600, but they didn't. T 0 equals 1620. The graph on the left shows the population increasing using a normal scale on the vertical axis. Because the population expanded into the millions, the data points represented years 1620 to 1700 are almost indistinguishable. In other words, I can't tell down here even close to what those values are. No idea. I know that they're growing, but it doesn't even look like they're growing at all because it's still really, really, really close to the x-axis. And even then, they start jumping, and finally they get all the way up here to like 7 million. I mean, that's why these numbers just grow so fast, but they don't grow very fast until we get to like 120, which is year 1740. This is 1600. No, this is 1620, 1640, 1660, 1680, 1700. 1720, 17, because it was off the 20s. It will be difficult to notice any differences in the population during those beginning years. The graph on the right uses a logarithmic scale. This is new to you. Base 10 for the vertical axis. Using logarithmic scales allow us to view all data points relative to each other. In 1600, it was somewhere around 100 to 1,000. This is 100, 10 squared. This is 10 cubed, which is 1,000. And then you can see it growing. It doesn't look exponential. It looks linear because this is exponential. So because these are exponential, this looks linear. Kind of follow? This is the way we're going to graph exponentials. So let's look at that again. Here's that graph on the right. The population of English Americans in the current United States for the years 1840, 1860, and 1880 are given below. Plot these additional data points on the graph above. This was 1620, 1640, 1660, 1680, 1700, 1720, 1740, 1760, 1780, 1800, 1820, 1840 is the 220. So 1840 is 220, and I'm supposed to be at 17 million. In 17 million, you got to know is going to be something like 10 to the 6th, somewhere between the 6th and the 7th. And so you go up between the 6th and the 7th and put a dot somewhere close to there. It's going to be an estimation, but it should still go up somewhat linear. It should be close to around in there. It should be not above 7 yet. And you got a calculator, you can do 10 to the 6th and figure out what that is, but it's 6 zeros. And 7 is 7 zeros. Then I'm going up to 31. at 40. And then 50. 50 million. And you're just getting close. Okay? That being said, you're never going to do something like this. You're going to do something more like this. This is called a logarithmic scaled graph. You're used to seeing rectangular. Every line represents 1 or 2 or 4 or 10. One common type of graph with a logarithmically scaled vertical axis includes grid lines seen below. The type of coordinate grid is likely to appear on the AP pre-cal exam. It's not likely, it will appear. I don't know why they say likely. I guess because it gets them out of maybe if they don't do it. Plot the following points on the same coordinate grid. 1, 20. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. 200, 300, 400, 500, 600, 700, 800, 900, 1,000. Kind of see how that's going? The first ones are going by ones, the second ones are going by tens, and the third ones are going by 100s. This is 10 to the first, this is 10 to the second, and this is 10 to the third. You probably will not see it as 10, 100. You will probably see it as 10 to the first, 10 to the second, and 10 to the third. But either way, you got to associate this stuff. Most students do a really good job with this. So 120 will be right here. Make sure you label it point A. If you just put it there and you didn't label it point A, you're going to get dinged because I don't know which point that is. 2, 300. Well, here's 100, 200, 300. And that is letter B. 3, 2. 1, 2. Because this is 10 to the 0. I'll see a lot of people put that on the second one. Be careful. This one's 1. It's not 0. You guys are used to that being 0. That's 1. Just like that one's 10. I didn't label that one. That's C. 4, 15. 4, that's 10. This is 20. 15's in the middle. 15 is between 10 and 20. That is point D. And the last one is 5, 350. 10, 100, 200, 300, 400, 350 is right in the middle. E. Take your time, get close. I'm not going to get a ruler out, but you ought to be close to being right in the middle. Any questions about a logarithmic scale? It's not that difficult. Most students do well. It's just something new to you guys. I never saw one until, I don't think I ever saw one in any of my mathematics until I took a summer class for this. So just a little bit different way of graphing things. Okay, y'all good there? Yep.
Why are they spaced out differently even though like each section is increasing linearly?
Yep. 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 Because that's the way they make them. I don't know. It does look weird, right? I don't know. It's just the way the exponentials. I don't know why those are not evenly spaced in between them. Okay, beautiful. All right, 10. Whoops, I didn't make that one big enough. There's that button. All right. Just as we graph previous functions, we can also graph logarithmic functions. So we know that this is a log base b of x, where b is greater than 0. B can never be 1. A can never be 0. Because if a is 0, the whole thing's 0. And if b is 1, you have 1 to any power, which is always 1. So therefore, and b will never be negative either. That's why it says b has to be greater than 0. That base will never be negative, and that base will never be 1. Because if it is, it's no longer logarithmic, it's now linear. Because exponential functions and logarithms are inverses of each other, we can also expect the characteristics of the output-input values of exponentials to become the characteristics of the output-input of the logarithmic functions. However, what was the output is now the input, and what was the input is now the output, because they're inverses. For exponential functions over equal length with input values, the output values change multiplicativity. I don't know, they multiply, right? 1, 3, 5, 7, that goes by 2s. 2, 4, 8, 16, this multiplies by 2s. So that's exponential. You guys already know that. Well, in a logarithmic, the y's will go by commons, the x's will multiply. And that's why I told you guys since day one, make sure you look at the x values. Make sure you look at the x values and make sure that they go by common numbers. Because if they don't go by common numbers, it's hard to see what y does. And in this particular case, the x's do not go by commons. The x's multiply and the y's go by the commons, and that makes it a logarithmic expression. Notice how the input values are changing, they're adding, while the output values are changing, multiplying. This is indicative of an exponential function. For logarithmic functions, these two properties are reversed. They're switched because they're inverses. In inverses, you switch x's and y's. Notice how the input values are changing multiplication, but the inputs, or the outputs, I'm sorry, are changing addition. This is indicative of a logarithmic function. So that's something else we're going to have to recognize, one of the others. We need to know if it's changing linear, quadratic, exponential, logarithmic. Selected values of several functions are shown below. For each, determine if it's a logarithmic, exponential, or neither. 1, 2, 3, 4, common. 16, 8, 4, 2, multiplied by 1/2, or divided by 2. So this is exponential. The input values are constant. The output values are being multiplied by 1/2, or you can say the output values are being divided by 2. B, 10 to 30, 30 to 90, 90 to 270. They're being multiplied, whereas this is going from 10 to 20, 20 to 30, and 30 to 40. That's common. This is logarithmic. Logarithmic. It's written right here. Don't write it like I did. You can on your homework on a test. I would not write log. Logarithmic. Don't write exp. Write exponential. Homework, I don't care. 550. 5,500. 500, 5,000. Multiplied by 10. 1, 2, 2, 4. 4, 8. Multiplied by 2. Neither. If both of them are being multiplied, it's neither. It's something, but it's not exponential and it's not logarithmic. Again, what were their questions? Logarithmic, exponential, or neither. So you don't have to worry about it what it is. You just can worry about what it's not. Yep.
So is logarithmic when the x value?
When the x values are multiplied. 4, 8, 8, 16, 1632 times 2, 1, negative 4, or sorry, negative 1, negative 4, negative 4, negative 3, negative 3. Good. This one is logarithmic. Yes, no? Okay. Recognize we're not done with these yet still this year. All right, beautiful. Now what do they say? F of x equals b to the x. G of x equals log base b of the x. In other words, this is exponential, this is logarithmic. This is an inverse of this. G is an inverse of f. F is an inverse of g. F and g are inverses. You don't need to tell me that, I know that. Therefore, f of g of x and g of f of x equals x, and we learned that from yesterday's lesson. Well, 2 days ago lesson. Recall 2 important properties of inverse functions. Graphs of inverses are reflections of each over the line y equals x. That's where it reflects over y equals x. If the point x1, y1 is on the graph of f, then y1, x1 is on the graph of inverse. Duh, we already knew that. That's why it says recall. Example, a number 2. F of x equals 3 to the x. G of x equals log base 3 of x. Show that f and g are inverses by showing that f of g of x equals g of f of x equals x. You'll have to do this on one question on the test on a free response. You'll have to prove it. I don't know what it's going to look like, but you're going to have to show that they're inverses. So f of g of x, that means I am putting this in place of that x. This becomes a little hard. So watch. Y or f of x, or however you want to say that. Let's say y equals 3, and not to the x, it's equal to the log of base 3 of x. Man. How's that written? Exponential or logarithmic? It's written exponential. 3 to the. So if it's written exponential, let's rewrite it logarithmic. And so rewrite it logarithmic. This is log base 3 of y equals log base 3 of x. That didn't help me. I see why now. I messed up. Gosh. How can I show you this that makes sense to you? Because some knucklehead's just going to cancel the 3 and the log base 3, and they're just going to cancel that out, and they're going to leave x. And that's officially not right. mean, it is right, but it's not right. Did I lose anybody on that, or yeah? Lost y'all? This simplifies to something, right? It simplifies to something. What does it simplify to? I don't know. 3 to what is equal to log base 3 of x? What does that question mark have to be? X. Because it's log base 3 of question mark is equal to log base 3 of x. In order for those to be equal, that question mark has to be a x. Okay with that? So that simplifies to x. I need to ask to make sure that you can't just cancel those things out and call that x. You can, but I don't know if you can just do that and they give you credit for it. Okay, bear with me. I'll come back on that one. There is a logarithmic rule that says if you have a base to log of that same base, that all just cancels out and you're just left with that x. But I don't know if I can just cancel that out and give you x without showing something. Bear with me on that. I got to do the flip of that. So now I have to put this in place of that x. So I have log base 3, not of x, but of 3 to the x. Okay? Three to what is 3 to the x? I'll be curious to see how you guys do on homework on that. Okay. A portion of the graph 2 to the x. Here's 2 to the x. I want to show the inverse of k, which is log base 2 of the x on the same coordinate grid. Again, to me, one of the easiest things to do is to find points and plot the flip of it. In other words, this is 0, 1. And if that's 0, 1, I'm going to go to 1, 0. There is 1, 2. So I'm going to go to 2, 1. There is, I'm sorry, I did that wrong. I can't see. Blind and stupid. This is 2, 1. 2, 1. That is 1, 2. Gosh dang it, get it right. 1, 2. Therefore, I got to go to 2, 1. 2, 1. This is what? That is 2, 4. I got to go to 4, 2. 1, 2, 3, 4, 1, 2. This is getting closer and closer to 0. This is going to get closer and closer to 0. This is going to get further and further away from the line. That's a logarithmic graph because that's the inverse of an exponential. You guys are better at that than me. Beautiful. All right, that's the last one. The exponential a to the x contains the points 2, 3, and 627. Okay, I guess it does. Find the average rate of change of y equals log base a of x from 3 to 27. This is where you start got to really think about what's going on. What type of function is this one? Exponential. What type of function is this? Logarithmic. What do we know about the difference between logarithmics and exponentials? They're inverses. And so if that goes from 3 to 2, 2 to 3, if it goes from 2, 3 to 6, 27, then the exponential has to go from 27, 6, and 3, 2. Okay? And so I want the average rate of change from 3 to 27. Well, ironically, here's my x values from 3 to 27. And the average rate of change is nothing more than y minus y over x minus x. And so I will simply do 6 minus 2 over 27 minus 3, and 6 minus 2 is 4, and 27 minus 3 is 24, and 4 over 24 is 1 over 6, and so the average rate of change from 3 to 27 is 1 over 6. Again, you kind of start thinking about, all right, if this is exponential and this is logarithmic, they're inverses of each other, so they just flip things. And if they can flip things, then I can just flip those values. And if I can flip those values, it's no longer y minus y over x minus x. It's kind of like x minus x over y minus y. Beautiful. I'll be curious to see is how you do on the some of this. I'll be curious to see how I did